Welcome to JB's Academy of Science. In this lesson, we are going to learn about electric field, electric field due to multiple charges, and problems on electric field. Electric field. We know that any two charges kept close to each other will interact with a force of repulsion or attraction depending on the nature of the charges. If they are like charges, they repel. If they are unlike charges, they attract. Now, if you bring a charge near to another charge, you will experience a force. Now, slowly, if you move the charge away from the other charge, you can see that force experienced by you due to the interaction of the two charges will decrease. If you move away, keep on moving away from the charge, the force also decreases, and beyond a limit, you cannot feel the force of interaction between the two charges. That is, any charge has a space around the charge in which you can feel or experience the presence of the charge. The space around a charge in which the presence of the charge can be felt or experienced, we can call as electric field around the charge. Now, consider the space around the charge. Take a point, any point inside the space. Place 1 coulomb positive charge. We say usually positive test charge. Then the strength of the electric field at this point, it's also called electric field intensity or simply electric field, is the force experienced by unit positive charge, that is positive test charge placed at this point. Now, if you place some charge at that point, it will experience some force. Then what is the force experienced by unit charge? Force divided by magnitude of the charge. For example, if you place a charge small q and it experiences a force F, then force experienced by 1 coulomb charge is F divided by Q. So this is the electric field intensity at that point. So electric field at a point is the ratio of the force to the charge placed at that point. Unit of electric field is Newton per coulomb. Unit of force by unit of charge. It has one more unit, volt per meter, which we will discuss in the coming lessons. Now, electric field due to a point charge. Consider a charge plus Q. Consider a point at a distance r from the charge Q. Consider another charge placed at that point plus Q prime. Now, there is a force between these two charges according to Coulomb's law, that is 1 by 4 pi epsilon 0 q dash divided by r square. Now, by the definition of electric field at a point is force experienced by unit positive charge or force by charge. So E is equal to F divided by Q dash is equal to 1 by 4 pi epsilon 0 Q dash divided by R square into 1 by Q dash. That is, E is equal to 1 by 4 pi epsilon 0 Q divided by R square. This is the expression for electric field due to a point charge. Remember, electric field is a vector quantity. It is ratio of force to the charge. Force is a vector quantity. Electric field is also a vector quantity. And here in this expression, E vector is equal to 1 by 4 pi epsilon 0 Q by R square R cap. R cap is the unit vector along the direction of R, which gives the direction of the electric field. Now we know that electric field is force by charge. And if you have an electric field, if you place a charge inside that electric field, what will it experience? Definitely, it will experience a force. This magnitude of the force experienced by a charge placed in an electric field is given by F is equal to Q into E. E is equal to F by Q, therefore F is equal to Q into E. So force is equal to charge into electric field. Electric field due to a system of charges. We have learned electric field due to a single charge. Now let us consider a group of charges or a system of charges. For our convenience, let us take Q1, Q2, Q3 and Q4, 4 charges. We have to find out the electric field intensity at point O due to the all 4 charges. Let R1, R2, R3, R4 be the distances of these charges from the point O. Then each charge will produce its own electric field at point O. Let us take E1, E2, E3, E4 respectively. The electric fields produced by Q1, Q2, Q3, Q4. Directions of E1, E2, E3, E4 is shown here. We can find out E1 plus E2 using parallelogram law of vector addition. The same way E3 plus E4 using parallelogram law of vector addition. Then again find the resultant using parallelogram law of vector addition. E is equal to E1 plus E2 plus E3 plus E4. Now, magnitude of the electric field at point O is sum of the electric fields due to all the charges Q1, Q2, Q3, Q4. That is 1 by 4 pi epsilon 0 Q1 divided by R1 square R1 cap plus 1 by 4 pi epsilon 0 Q2 divided by R2 square R2 cap plus 1 by 4 pi epsilon 0 Q3 divided by R3 square R3 cap plus 1 by 4 pi epsilon 0 Q4 divided by R4 square R4 cap. Now, if there are n charges in the system, then the resultant electric field due to n charges is given by 1 by 4 pi epsilon 0 Q1 by R1 square R1 cap plus 1 by 4 pi epsilon 0 Q2 divided by R2 square R2 cap plus etc. up to 1 by 4 pi epsilon 0 Qn divided by Rn square Rn cap. Using sigma notation, we can write E vector is equal to 1 by 4 pi epsilon 0 sigma I is equal to 1 to n Qi divided by Ri square Ri cap. That is, the net electric field due to a system or group of charges is the vector sum of the electric fields due to the individual charges. Since electric field is a vector quantity, remember we have to take the vector sum. Uniform and non-uniform electric fields. Consider the space around a point charge plus Q as shown in the figure. In this space, consider any 4 points at 4 different distances from this charge Q. Now, let E1, E2, E3, E4 be the electric field intensities at these points. What do you think about the magnitude of these electric fields? Are they same? Of course, they are not same because distance of the points is not same. Therefore, electric field also will be different. Now, take another arrangement of electric charges. We have a positive charge and a negative charge arrangement. A parallel arrangement of positively charged plate and a negatively charged plate. Now consider any 4 points inside the space. In this case, you can see the electric field intensity at any point inside the space between these two charges will be same, unlike the earlier case. Then, if you can create such a field in which the strength of the electric field is same at all points, it is called a uniform electric field. Example for a uniform electric field is an electric field created between two charged parallel metal plates. If you take two metal plates kept parallel to each other and both the plates are charged by opposite charges, then the space between them will be uniform electric field. Now, if electric field intensity at all points in an electric field is not same, then what do you call it? Is a non-uniform electric field. So if you have a positive charge and negative charge, then the space around them will be an example for non-uniform electric field. Electric field intensity will not be same at all points. Now let us do some problems based on electric field. Find the electric field intensity at the midpoint of the line joining two charges of plus 4 millicoulomb and minus 4 millicoulomb separated by a distance of 2 meter in free space. So consider the charges plus 4 microcoulomb, plus 4 millicoulomb and minus 4 millicoulomb separated by a distance of 2 meters. Now, if you take the midpoint on the line joining the two charges, each charge will be at a distance of 1 meter from the point. Now, we know that electric field due to a point charge E is equal to 1 by 4 pi epsilon 0 q by r square. Now, if E1 and E2 are the electric fields produced by each charge plus 4 millicoulomb and minus 4 millicoulomb at P, E1 is equal to E2 here because magnitude of the charges is same and distance of the point from the two charges is same. Therefore, E1 is equal to E2 is equal to 9 into 10 to the power of 9 into 4 into 10 to the power of minus 3, that is 36 into 10 to the power of 6 Newton per Coulomb. In this case, electric field at P due to plus 4 millicoulomb is towards the point and electric field due to minus 4 millicoulomb is away from the point, that is from the point to the charge. So, therefore, both the fields E1 and E2 are in the same direction. Therefore, the resultant field is E is equal to E1 plus E2, that is 72 into 10 to the power of 6 Newton per Coulomb. Next problem, 2-point charges plus 8 microcoulomb and plus 12 microcoulomb placed in free space at 60 centimeter apart from each other. Find the position of the point between them where the electric field is 0. So consider plus 8 microcoulomb plus 12 microcoulomb separated by a distance of 60 centimeter. Consider a point P between them where electric field is 0. Let x be the distance of the point P from plus 8 microcoulomb. Then the remaining distance will be 0.6 minus x. We know that E is equal to 1 by 4 pi epsilon 0 q by r square. At point P, resultant field is 0. E1 is equal to E2. That is 1 by 4 pi epsilon 0, 8 into 10 to the power of minus 6 divided by x square. That is E1 is equal to 1 by 4 pi epsilon 0, 12 into 10 to the power of minus 6 divided by 0.6 minus x whole square. Simplifying and solving for x, we will get x is equal to 0.269 meters. That is, the point is 26.9 centimeter from plus 8 microcoulomb charge. Next problem. A proton is placed in a uniform electric field set up vertically. Find the magnitude and direction of the field to keep the proton stationary in the field. Given the mass of the proton is equal to 1.672 into 10 to the power of minus 27 kilogram and the charge of the proton is equal to 1.6 into 10 to the power of minus 19 coulomb. Acceleration due to gravity g is equal to 10 meter per second square. Here, to make the proton stationary, the upward forces must be equal to the downward forces. Weight of the proton is acting downwards. Electrical forces on the proton is acting upwards. So electrical force on the proton is equal to weight of the proton. That is, E into capital E is equal to mg, or electric field capital E is equal to mg divided by small e. That is 1.045 into the power of minus 7 Newton per Coulomb. Direction should be vertically upwards since the charge of proton is positive. Next problem. 4 charges plus 8 microcoulomb minus 8 microcoulomb plus 5 microcoulomb and minus 5 microcoulomb are kept at the 4 corners of a square ABCD of sides 10 centimeter. Find the electric field at the center of the square where the 2 diagonals meet. Look at the figure. A square ABCD. The charges are kept at the corners ABCD respectively. O is the center of the square where 2 diagonals meet. The distance of each charge from the center O is equal to 5 root 2 centimeters. The electric field at O due to the charges at A, B, C, D respectively, EA is equal to 144 into 10 to the power of 3 Newton per Coulomb. EB 144 into 10 to the power of 3 Newton per Coulomb. EC 90 into 10 to the power of 3 Newton per Coulomb. ED 90 into 10 to the power of 3 Newton per Coulomb. Now, EA and EC are in the opposite directions. Therefore, E1 is equal to EA plus EC, that is 54 into 10 to the power of 3 Newton per Coulomb. Similarly, E2 is equal to EB plus ED is again 54 into 10 to the power of 3 Newton per Coulomb. Now, we can find out the resultant field by applying parallelogram law of vector addition or using the equation. The net electric field E is equal to root of E1 square plus E2 square. E1 and E2, they are perpendicular to each other. So we can use the equation. E is equal to root of E1 square plus E2 square is equal to 76.37 into 10 to the power of 3 Newton per Coulomb. Thanks for watching the video. More videos will be uploaded soon. Kindly watch and comment the suggestions in the comment section of the video. Thank you all.